Hi everyone. I'm Courtney Amberger, and I'm going to be talking today about my project on predicting harvest residue moisture content using the fire indices. So a bit of background on the topic. New Zealand is currently moving towards a low carbon future. So an initiative called the Carbon Neutral Government Program was launched by the government in December 2020. And it aimed to make a number of organisations within the public sector carbon neutral from 2025. In this program, there's a section for emissions reduction, with energy and industry being a focus point. The goal of this section is for 50% of total energy consumption to come from renewable sources by 2035. Biofuel from renewable sources like these production forest harvest residues are one of the potential sources for this. The issue is that current research in the area considers all residues to have a constant calorific value year-round. We know that moisture content in the residue changes seasonally, which means that the calorific value of these residues changes as well. Because of this, current estimates for energy content from the residues are not as accurate as they could be. Being able to predict these moisture content values more accurately will give a better representation of the energy available from harvest residues. The current energy content value that's used is usually around 6 to 7 gigajoules per tonne, which considers a moisture content of around 50%, so around about greenwood, while drywood has an energy content of about 20 gigajoules per tonne. So this study aimed to find a correlation between one or more of the New Zealand Fire Danger Rating System fire index codes and the moisture content of harvest residues. From there, once that relationship was found, a temporal estimate was created for the energy content of forest harvest residues using that moisture content. So the Fire Danger Rating System in New Zealand is based off the Canadian system, and it's got 4 main components that make it up. So you've got the Fire Weather Index system, the Accessory Fuel Moisture system, the Fire Behaviour Prediction system, and the Fire Occurrence Prediction system. So I focused on the Fire Weather Index because that was surrounding weather and inputs like that. So that was made up of the 5 codes that you can see up here. So the first one, the first 3 up here are fuel moisture codes. So the fine fuel moisture code represents the relative ease of ignition and flammability for the first soil layer in the forest. So this is things like grass or pine needles that are on the ground. The duff moisture code is the next layer down, and that's the loosely compacted duff layer. So that's a medium-sized fuel as well. The drought code is the deepest layer, and that's organic matter and the largest fuels. The initial spread index and the build-up index are both fire behaviour indices. The initial spread index represents the expected rate of fire spread, while the build-up index represents the total amount of forest fuel available for combustion. The initial assumption of this project was that it would correlate best with either the build-up index or the drought code, because these are the 2 fuel sizes or relative fuel sizes that I was looking into. So for data collection, it was spread across 2 sites in the Nelson region so that I could get a range of fire index values. These sites were selected by being relatively spread in the Nelson region, and I also wanted to make sure that they were close to weather stations so that the fire index data that I was getting was relative to the logs, the sites. The Dovedale site was an exposed, recently harvested forest, while so that was this one here. And then this one here was the higher site, which was mature pine. So that site was blocking out a lot of the wind and any factors like that. So I used 48 logs in total, 24 of which were harvested in 2021. So these logs were a year old, and they were used for my aged relationship. And the other 24 were from a 2022 harvest, and they were about a month old when the project started. They were separated to determine differences between the reactions to the fire codes, although this point was not identified in the project because it didn't go on for long enough. This could be a point that's looked into further. The log 1.5 metres in length, and the diameters ranged between 10 centimetres to 25 centimetres. The logs were labelled individually so that the moisture content of each log could be tracked. And the moisture content was taken initially using destructive sampling, and then still going. They were taken to the uni lab, and then the gravimetric method was done on those. So they were weighed twice a week, and the indices were recorded for every time they were weighed. So this is the raw data that I got from the study. This is only for one of the sites, but they both had the same trends. So this is probably one of the more interesting finds that I think I found with this project. So these are the aged logs, so the ones that were harvested in 2021. And you can see that there's quite a few spikes in it where the moisture content will increase. This was when there was quite high rainfall in the area, and you can see that the green logs just have a continual trend down. This was found to be because of the moisture content gradient in the logs. So using that data, I did linear regression and managed to find these two relationships. So both of them correlated strongest with the build-up index, which was as expected. The aged correlation was obviously a lot stronger than the green. And because of this, only the aged correlation was used further in the study, as I didn't want to carry through errors from a weaker relationship. So the data available on the FENS website for the historic build-up index data range from 1993 to 2021. So over these 28 years, I averaged every single day to get an approximate trend for what the build-up index is going to do. And as expected, it was a lot higher in the warmer months than the colder months. Build-up index was then applied to the relationships that I showed in the previous slide. So this is including 95% confidence intervals. And this gave a moisture content through the year. And then I applied a relationship to get the energy content. So then you can see I've got the 95% intervals here, and it results in a range between 10 to 14 gigajoules per. So a couple of things to think about from this study is the supply chain, the effects of decay, and the energy usage trends. So I noticed towards the end of my study that there were significant amounts of bugs, insects, and fungi type things on the logs. And this may impact the relationship with the build-up index. I'm not sure when this point is that it starts affecting it, but this could be, if the study was carried out longer, this would maybe find the end point of how long you can use that aged relationship for. For the supply chain, the publicly available data for the volumes of harvest probably isn't quite accurate enough to be guessing regionally how much you've got available, but it could be something that's used sort of per company to see what they could be providing. One more minute. Oh, sorry. And another thing is the energy usage trends. So comparing it to what we're actually expecting our energy to do, or our coal usage, because that's what we're aiming to replace with these biofuels. So in conclusion, I found two relationships, both of them with the build-up index. The age relationship had really good correlation at 0.95, but the green wasn't quite as strong. And it resulted in an energy content range between approximately 10 to 14 gigajoules per tonne compared to the 7 used previously.